Horti-BlueC is funded by the European Regional Development Fund under the Interreg 2Cs programme. Horti-BlueC aims to create a more sustainable, circular and soilless horticultural process.
By continuing the trials, Horti-BlueC aims to achieve two of the main goals of the project: optimising the biochar production to produce an efficient growing medium, and improve the CO2 capturing and cleaning process to reuse CO2 in greenhouses. This will ultimately lead to a decrease in the use of chemical crop protection and fertilisers, reduce CO2 emissions, and provide new circular economy solutions in the 2Cs area.
So, hello everyone, and a very warm welcome to the first of the Horti-BlueC webinar series. And today we're going to be talking about large-scale gasification for energy and biochar production. My name is Cressida Bowyer. I'm a senior research fellow at the University of Portsmouth, and I'm one of the researchers working on this project. So Horti-BlueC is a multi-partner project supported by Interreg 2Cs, and we're developing a sustainable greenhouse model for commercial horticulture. So we're going to hear from three project researchers, and as I say, then we'll have a short discussion. So let's now begin with a brief introduction to the energy and biochar valorisation chain from the project lead, Dr. Bart van der Kasteel.
Thank you, Cressida, for introducing me. Okay, welcome in this first webinar, and I will shortly introduce the valorization chain that we will discuss today. So it's the first valorization chain that we developed within this project. And we had actually 5 waste streams that we wanted to upcycle during this project. And for upcycling, we selected several processing options to make building blocks for sustainable growing media. So for each of the waste streams, we had to select the most optimal processing option to come to the best quality of the building block. So for today, we will present the first valorization chain that we have developed. So it means that we will go to large-scale gasification of mainly woody biomass because it allows us for CO2 reduction and also for biochar production in combination with energy. So we will start from the woody fraction of green waste compost and also from plant fibers. The other waste streams that we have selected for valorization chains will be covered in the next webinars. So we will also process shellfish waste into chitin. That's the second valorization chain. And also we will try to upcycle spent growing media directly for reuse or as biochar of compost. So that's the third webinar. And the last webinar in fall of this year, there we will select new materials for renewable growing media blends. But today we will focus on the first valorization chain. So we start from woody fraction and plant fibers, and they will be processed by gasification into energy, into heat, and into biochar. And the biochar then can be used in growing media as bulk replacement for other materials. And it can also play a role as fertilizer or can even help plants for having a higher disease suppression. So what is the baseline scenario we start from? Well, we start from heating greenhouses with natural gas, while in the new scenario, we use large-scale gasification, where energy is produced together with biochar. And this energy production is quite important for the economic aspects of this valorization chain because it allows the processor to have revenues. And the energy can, of course, be used for lighting greenhouses and for heating these greenhouses. For having this good energy balance, we start with optimal feedstocks being woody biomass, miscanthus straw, or flax chives. And then biochar is used for bulk replacement and growing media. So the societal pressure is the replacing of natural gas by this renewable energy, and the implementation can be done in 5 years from now. So this webinar is really focusing on woody feedstocks for producing biochar and on bulk replacement and growing media. This is in contrast of the to the topic in webinar 3, where we will start from spent growing media and we will focus on other applications. Here you'll see one of the biochar production installations at ECN TNO. So they have different installations they use in the upscaling process for the biochar production. So I would like to thank you for your attention for this introduction. And we now move to the next topic.
Thanks, Bart. Next, we've got Dr. Rian Visser from TNO, who are an innovation organisation in the Netherlands who carry out applied scientific research. And Rian's going to tell us about biochar production. And her presentation is going to start with a short film about the biochar production process at TNO.
We provide the biochar to a substrate mixer or company that mixes it into substrate mixtures, and they go into plant trials. And so far in the different projects we've had, I think our biochar has been a big success in that it can really replace large percentages of peat. And peat, as we know, is not all that sustainable. So replacing peat is one of the big goals in this project. Well, this is one of the installations where we make partially energy, bioenergy, and partially biochar, because we believe this is actually the most sustainable way of doing it. And in this one, for instance, we've used also spent substrates from the greenhouses. So we can actually make a biochar from spent material. We have 3 installations, so you're looking at the smallest one. This is an installation that is actually one big screw, so it takes the material from where it enters into the reactor for a certain amount of time, usually half an hour, and then it's dropping into this collection bin, which is changed every now and then when it's full. And this is a very easy way that can actually handle nearly all types of feedstock. But for the woody types and say the reed types, we also have bigger installations where we can make larger quantities. The biomass comes actually from a bunker on the top, and there it falls into this big screw which moves at a very slow pace, bringing it in about half an hour to this exit where the solid biochar is collected in the bins. The gas that is produced, because nearly 80% of the biomass will result in bioenergy, that is taken away and be treated somewhere else. This is actually the material that we start with. This is the spent peat material coming from the strawberry growing of last year. And when it's gone through the facility, this is what comes out. And this looks really nice. This should go back in to growing new strawberries next year. So different feedstock, like there is some that are flax, miscanthus, which is a giant reed. Then there is the different kinds of wood. There is bark, and then there is different conditions. We very much work on getting better quality all the time and experimenting on how to achieve this. So one of the 2 things that are proven to be very important is the residence time. How long is it at a certain temperature, and the maximum temperature. So these are the key factors for good quality. And getting a biochar that's actually free of tars, because this is often not the case. The biggest challenge at the moment is making larger quantities, as there is a number of greenhouse trials that is going to happen in the next year. And at this scale, we cannot provide enough biochar. So going for a larger scale installation, producing larger quantities is our next step.
Welcome, everybody. It's very nice that you all came to have a good idea about how to produce biochar and bioenergy. I try to explain as good as I can. I've seen that we have quite a wide range of expertise in the group of people in the audience. So I I put in a few extra slides to try and explain it to everybody. So the content of the talk will be about biochar production technologies, but also on the quality of biochar, the total co-production concept, then some environmental issues, cost price calculations, since you had a lot of questions on the cost price, and also a few slides on legislation. So let me tell you first why biochar plus bioenergy and why at a very large scale. Well, you can make biochar by pyrolysis, which is only heating of the feedstock, and by gasification, which is using some air or steam or CO2 with too little oxygen to burn everything. That is the very simple explanation. At the elevated temperature, the biomass feedstock then degasses, all the gases come free, and this gas is a burnable gas. So from an environmental point of view, it would be stupid not to use this as an energy source, and it can replace fossil fuels. It prevents environmental unfriendly gases that would go to the atmosphere and would be a lot worse than just the CO2 if you would burn it all. So from an economic point of view, it would also be stupid not to use this gas as an energy source. So it adds to your revenues. So you simply have two products that have a positive value. And of course, then you have a more viable economic situation. So why the larger scale? So the production of biochar at the moment is too expensive for nearly all its market applications, including the bulk replacement of peat in horticulture. But that is something we want to do something about. So one way to reduce the price is the economy of scale. So a good scalable technology is when twice the size does not cost twice the price. So the larger scale will cost you less. So scalability has been an important issue in the technology choice. The larger scale also means less heat losses and more energy to sell. So it is economically and environmentally profitable. So the right size also depends on the bioenergy, usually heat, which can be used. So how many hours in a year can it be used and how many megawatt hours can be used at a certain location. So to put it a bit in perspective, for a greenhouse location, we would aim at something like 15 megawatt thermal input. That is about 20,000 tons of wood and roughly 4,500 hours of heat requirement. But for an industrial location, you could go to a bigger size and use the year-round 8,000 hours. And that would still be small enough to allow for local sources of bio residues. So this puts it a bit into perspective. And then what did we use so far in the project? Well, we used all sorts of different installations as we have a nice range. As you saw in the picture, the video, we used the screw reactor, which is our smallest one. But we also had a moving bed reactor, which is slightly bigger. We tried bubbling fluidized beds, which we in the end decided was not such a good idea. And we finally decided on gasification on the grades. We had different sizes. Sometimes the smallest one is just 3 kilograms per hour input. And at the moment we're using 30 kilograms per hour on input. It resulted in different yields of biochar. So we've been as low as 5% for the fluidized bed, which was the main reason that we didn't continue with it. And you can go to up to 35% on the screw reactor, but more is not always better. And we use different temperatures and different residence times and different feedstocks. And all in all, we have now more than 10 years of experience on making a good quality biochar. And the bottom line is you can get a good biochar out of all these technologies. So the technology in itself is not the key factor. We use always gasification because a little bit of oxygen will give you a better biochar quality. And you have to pay attention that you will not allow chars to precipitate back on your products. Now, what does make the difference in these technologies? This is basically the economy. It's the yields, it's the quality, and it's the energy recovery. And there are major differences, which will be also an issue in the rest of this presentation. So about the quality of the biochar, I think what we've done in this project is, and we've done this over the last 10 years, is to make the biochar to make the biomass, I have to say, at the beginning already in the size that you want your product to be. And this is, of course, in discussion with your client, because it has to be put into a mixture in this case for the substrates, and it has to fit the rest of the mixture materials as well. So the size is dependent on the client. And then you see some nice pictures on the top. You see wood, and the larger scale and the more detailed scale, and at the bottom you see some miscanthus. So in general, we have a lightweight product, which might only weigh something like 100 to 140 kilograms per cubic meter. And if you use wood, it is very low in ash. It holds roughly 4 times its own weight in water, but that is just contained in the pores because it is not flexible. It's not like peat anymore. Then we follow the qualification of the European Biochar certificate. We've always done this, and I think it's important to stress that qualification is important. So they have a number of requirements. The first is that you can only call it biochar when your carbon content is above 50%. And then they have 2 ratios, the hydrogen over the organic carbon and the oxygen over organic carbon. And these are just expressions that say that you've been degassing to a large degree, so that you didn't have a lot of the gases still in the material, but you've been going through the process and made this burnable gas, and it's freeing up all the pores, and then you get this nice structure I just showed you. And I think one of the most important things I've seen so far in this decade I work on it is the sum of the polyaromatic hydrocarbons. And these are a sum of 16 selected by the Environmental Protection Agency in the US, but doesn't matter really. It's the most important hydrocarbons summed up, and that has to be below a certain threshold. So the European Biochar certificate has determined smaller than 12 milligrams per kilogram biochar is qualified as good, and smaller than 4 milligrams per kilogram is a premium quality. Then there is a threshold on a number of heavy metals, also can be qualified as good or premium. And then the PCBs and the dioxins have to be almost below detection limit. Then at least 70% of the heat must be used to be called sustainable. And then in the green, you can see the quality passport of our TNO biochars. And if you compare them with the European Biochar certificate, you can say that we made really excellent biochar so far. We go only for good quality. We don't want to compromise on anything that goes into food production. It can be different, and this is what I show you. This is in the early years in a project that we did also with a number of the partners in this project called Fertility+. And what you see here is on the left side, the pyrolysis biochars that we made at a very early stage. And this are the tars. There are different tars, but all in all, they end up to this sum of the EPA tars. And on this left axis, then you see the milligrams per kilogram of the total of the stack. And what you see is that we had problems for the pyrolysis biochar in trying to keep them at the right level. So this would be good, but this wasn't, and it was difficult. So that's when we decided to go to gasification, and this is all this range, which is only for this period in the Fertility+. And you see that every location there is a sum, but at some locations it's very small. So in general, we learned to make biochar, which was well below the 4 milligrams per kilogram. So what are the large bars? This is something why I show you this picture, is these large bars are from the cyclone. This means that it has been traveling with the gas, the burnable gas. And if you try to harvest this black stuff, it's no good. It's always chock full of tars. And this is just to show you, these are often from the same experiment, So this would be the biochar we harvested, and this would be the biochar going, or the char going over the top with the gas stream that is filtered off somewhere, but it's full of tars. So this is just to give you an indication where you could go wrong. And the total concept that we foresee for now for entering the markets is this NHR concept with the co-production of bioenergy and biochar. So you have some bioresidues. This could be wood clippings, or they could be food residues if they're somehow a bit woody and fibrous. It enters the reactor, then it is gasified, and the gas will travel to the top. You follow the arrows, and there you have the heat exchangers where you can make heat. And if you want, if it's bigger, also electricity. From the chimney, you could take the CO2, you have to clean it. It could go to the greenhouse, or it go to storage as carbon storage. But at the bottom of the installation, here you harvest your biochar, and you can use it as a peat replacement in potting soil. And also very important, after this life as peat replacement in potting soil, you can reuse it to a number of occasions probably, but then it can go as carbon storage also into soil. This is to show you that a high yield in biochar gives you less energy, and also often a very poor quality of your biochar in terms of porosity and surface. So if you make it at lower temperatures, like this indicated here is the 400 degrees produced, these in the columns, you see that the relative yield of biochar is highest of all. And then it's not the best quality. And what's more important even, your quality of the gas, so where's my cursor here, which is representing the lower heating value of your gas, is also not as good as that you would go to maybe a bit less yield in the biochar and a higher energy value of your produced gas. Also, the ash content is important, and then you see the spent coir, which is used for strawberries in the UK, and also the used peat here in the orange. They have a higher ash content, and therefore they result in lower gas quality, because a smaller part of the product can be used for energy generation, as the ash will just come out as ash. Then I want to bring up some environmental issues, because we do this all also for environmental benefits. So if you look at this picture with numbers from NASA, you see the human emissions, which in scaled in perspective to the rest is a fairly small number. And you see that these human emissions have gone partially to higher photosynthesis, partially it has also been taken up into the upper part of the sea. And the rest is actually leading to climate change. So this small number is still relevant. The good news, I think, is that this cycle, which you see here, by photosynthesis, plant respiration, microbial decomposition, but also soil carbon, has the potential to store a lot. There we can easily store some of the carbon that we make, and the potential of storing it in the soils that we have is huge. And it's also been established that it can be done because you have this terra preta, which you may have heard of, which are in the Amazon, some very good soils they found where biochar was incorporated and which lasted for thousands of years. So if you make the biochar at a higher temperature, it's more stable. And then if it's more stable, it will stay longer in soil. So there's some current literature consensus that if you make it at high enough temperature, then after 100 years, roughly 30% might have oxidized to CO2, but 70% is still carbon in soil. Therefore, used as a substrate with the biochar, after use, it can be regarded as a carbon storage option. When, for instance, mixed with compost, it will be used in the fields. You do more than just the climate change if you do a life cycle assessment, because you don't want to solve one problem, for instance, the climate change, and create another problem, maybe by making more pollutants in water or air or in solids. So we published before a paper on a life cycle assessment in which biochar replaces peat in horticulture, together with my colleague Lydia. And in that case, we compared, this is an important issue in life cycle analysis, the reference system where we heat the greenhouse with natural gas. And we compared 1 megajoule of fossil heat compared with the system of Enerchar, where we use biochar for gasification and heating and producing biochar for the substrate. And then you avoid to a certain amount the extraction of peat. And this is one way of doing it. And you can just read up on the paper that we have. But we thought it would also be nice, as we are working with greenhouse growers, to make an LCA based on a functional unit of 1 kilogram of tomatoes. And we're still in the process of doing this. But here we already have the CO2 equivalents for the climate change. And what you see is, I've called it current common practice, at least in Holland and in Flanders, I think, where the tomatoes are grown on a peat substrate and heated by a local natural gas heater. And they use an electricity you take off the grid. And in this case, we've taken the burden as it is created by the Dutch energy mix. So you can see that the heat has a huge impact, but also the peat, the green part, has a significant impact. It's not negligible, definitely not, even though it's much smaller than the heat. And the impact is 0.92 kilograms of CO2 equivalents for a kilogram of tomatoes. This is huge, almost a kilogram of CO2 for a kilogram of tomatoes. And then on the right-hand side, you see the difference with the Enerchar concept, where we use the biomass for heating. And if you store after use in the greenhouse your substrate with the biochar in the field, then this green bar now is below the zero. So below zero means it's a negative emission. You actually stored carbon. And therefore, this is definitely showing you a much smaller number in emissions, 0.38 kilograms of CO2 equivalents per kilogram of tomatoes, which is a huge change compared to the common practice. We also compared, what if you, at the moment, capture the CO2 from the chimney and you store it underground? Maybe you've seen the news if you are from the Netherlands. The pipeline is going into sea finally from the big oil companies and refineries. They are going to store it. So there should be a possibility within long. And now this whole blue section shows you a negative emission if you take the CO2 out and bring that to a underground storage. So now you see that you both have a positive contribution from fossil energy on making heat. But if you take the CO2 from the chimney, then the blue part will show you that you can subtract it again. If you do the same for the Enerchar concept, you can see that you can go to real low numbers if you also take the CO2 that you produced with the heat from the chimney and bring it underground. Of course, you could also use it in the greenhouse, but we've chosen to model here because it was nicely available in the LCA program to store it underground. If you then put all these four numbers together and you multiply it by the number of tomatoes grown in the Netherlands, which is quite a lot, then you can see that this is the common practice. I've just called it CCP for short. And you can see here the potential of reduction. This is with just storing of the CO2, which halves it already. But the Enerchar concept can bring you as much as 80% of reduction. if you also take the CO2 from the chimney and bring it underground. So the inner char concept has the potential of a very significant CO2 emission reduction by replacing fossil heat, plus storing biochar in soil after use in the greenhouse, plus capturing the CO2 at the chimney and storing it underground. So with that, I would like to conclude my first part. And later on, I want to tell you something about the cost price and the legislation with respect to biochar. Okay.
Thanks, Rianne, for your really nice presentation, really highlighting how the circular economy can be used to like reduce waste, whether it's solid waste or gaseous waste, and that carbon capture element, and you know, ending up with like halving or more of the carbon footprint of tomato production. Yeah, and now back to Bart, who's from ILVO, which is the Flanders Institute for Agriculture, Fisheries and Food. And Bart's going to tell us about the chemical and physical properties of biochar that we've produced in the Horti-BlueC project.
Okay, thank you, Cressida. So we have analyzed the biochars that were produced by ECN-TNO for the project, and here are some important results. So we start with a poll actually. So when we go from a feedstock to a biochar, yeah, several things can happen with the total concentrations. They can increase or they can decrease, and they can increase by a factor of 2 to 5, or maybe only by a factor 3 to 4, or they can decrease with the same factors. So the poll is now, we would like you to answer the poll that will appear in a moment on the screen, and you can answer what you think that happens when you go from feedstock into biochar with the total concentrations. So that's actually what we have tested. We have gone from flax chives to biochar, or from miscanthus. And here you see some the results of the poll. So most of you said that concentrations would increase by a factor 3 to 4. So you are all actually biochar experts already. So because that's the right answer. So we see, of course, that the pH of the biochars is higher than for the feedstocks. Yeah, the electrical conductivity can be a little bit higher, but mainly for the macronutrients, we see a quite strong increase by a factor 3 or 4, with a higher increase, of course, for the higher gasification temperatures. So when we use biochar in a growing medium, we have to take care that the circulation of water and nutrients and the recirculation and greenhouse cultivation is not affected by using this biochar. So for this, we had done several tests. For instance, we have checked the cation exchange capacity of the biochars that we have produced, and we have compared them with peat. And we have seen that this exchange capacity is somewhat lower for biochar, but there was a very strong effect of the feedstock that we used. When we checked the porosities of these materials, we saw that biochars have a fairly high porosity, which is quite comparable to peat. So here there might not be really a problem in terms of porosity. And then when we check the interaction with nutrients and the fertigation solution, we know that peat can have a very strong potassium retention, mainly in the beginning of the cultivation. So we checked it also when biochar was partly replacing the peat, and we saw that this retention was much lower. And in some cases, biochar can also be a source of potassium for the plants or for the fertigation solution. So then we come to the other important topic. It's the pH of the biochar. And for testing the net effect of biochar, we mixed it with sand and a 10% volume ratio. And we would now like you to answer the question whether the pH is decreasing or increasing after mixing the sand with biochar, and how big or how large this change is. Okay, again, I see that we have a lot of biochar experts already in the webinar, so it's actually the right answer. So for the woody biochars that we have produced, we saw that the pH increase was maximum 1 pH unit, However, we have to take care because we have two kinds of carbon. We have the black carbon and the white carbon. The black carbon, it's the organic carbon, and the white carbon, it's the inorganic carbon. It's the calcium carbonate, as we mostly call it. And this calcium carbonate, it causes buffering against acidification, which when this buffering capacity or when the inorganic carbon content is low, it's okay, because then you can use the biochar as a lime replacement in growing media. However, when this buffering capacity is very high, it can make your blend having a pH above the optimal pH for plant growth. So that can be a problem. But for biochars from a woody feedstock, we saw that pH was between 8 and 9.8, which is quite high, while they had a very low inorganic carbon content. And as a result of that, we saw that the pH increase caused by this biochar addition was only 0.5 pH units. On the other hand, when you have biochars with a very high inorganic carbon content, this pH increase can be much higher. So in that case, you really have to take care on the volume that you apply and the growing media blend. So the last aspect that we wanted to check is that the inherent quality of the biochar to be used in growing media blends. So we had a suitability score that we have applied, and it combines 8 important characteristics of materials to be used in growing media blends, and they were scored between 0 and 2, and the sum was then, of course, maximum 16, which indicates a very high quality or very high potential for use in growing media. And we saw that the biochars from a woody feedstock, they had a fairly high score of 10 to 13, which means that they really, you can really use them in growing media without any potential problems. So thank you.
Thank you, Bart. And next, Laura Goldstein from Milvo is going to tell us about some of the Horti-BlueC biochar greenhouse trials.
Good afternoon. I will shortly present to you some results from greenhouse trials with growing media containing biochar. As it is not the focus of this webinar and many of the trials are still ongoing, I will not elaborate on details, but I just want to illustrate the main effects that are seen in the trials. So trials are being done on lab scale, pilot scale, and commercial scale by several of the project partners on different locations. So the partners test the newly developed growing media in greenhouses for both strawberry and tomato cultivation. For strawberry, these new growing media are peat-reduced blends with 40% peat replacement. And for tomato, these new growing media are peat-free blends. So the peat-reduced blends for strawberry contain wood fire, coir, and compost. And to some of these blends, biochar was added as an amendment, and to others more as a bulk replacement in higher amounts. So when running the greenhouse trials, the performance of the new blends was always determined relatively to the performance of a control blend. And for strawberry, this control blend is a mix of peat, coir, and perlite. The performance of the blends was characterized by the effect on parameters such as yield, fruit quality, but also the resilience to pests and diseases. For tomato, the blends were peat-free, and they also contain wood fiber, coir, and compost. And biochar was added in different amounts to the blends, sometimes in combination with chitin, and sometimes in higher volume percentages as a bulk replacement. For tomato, the reference is peat coir grow bags or rock wool, and the same parameters were measured to determine the performance of the new blends. So what was observed in the greenhouse trials with biochar, with strawberry and tomato? Well, in general, the sustainable new growing media blends performed very well in the greenhouses. On a side note, for optimization, some technical and management adaptations may be required. Biochar can help to improve the performance of the new growing media blends, and mainly under conditions of reduced input of nutrients. And biochar can be used for bulk replacement without great implications. So if you would like to get more detailed and technical results from the trials, join one of our Horti-BlueC open events in August and October.
Great, thanks, Laura. In a couple of minutes, Rianne's going to tell us a little bit more about the cost and legislation around biochar use and production. But first of all, we're going to see another short film which describes how biochar production is being upscaled at TNO.
May 4th, 2021. And yes, we've started up at the larger scale, the pilot scale, Enachar, to make biochar and bioenergy. Here to see from the drawing, this is a screw and it takes the fuel into the reactor where it goes on the steps of the great reactor and it degasses and finally the biochar will fall into the bunker. Very difficult to get a good overview, but this is the bunker where at the moment we only have beach. This is very nice fuel to make it technically easier. But we will go to Miscanthus and spend growing media afterwards. This is the fuel bunker, and from the fuel bunker it is fed via this fuel into another container, and then it's taken into the reactor, which is the big vessel you see here behind me. This is the middle section where we bring in air to burn the gas, and from this burned gas you can make electricity or use the heat. This is the top section of the reactor. It's where the cooler is hanging down. It cools the gas, and after cooling it is treated outside and cleaned before it goes off to the chimney. This is the bottom of the reactor where it will come out. The biochar being transported upwards towards the collection bin, which is changed every now and then when it's full. This is the first biochar we made of the day, so it's really nice, looking good. And we're hoping to make a lot more of these bins in the course of the day for a larger scale trial. The video you just saw was just made by my cell phone last week, but very kindly by other partners put together to give you an idea that we've really started up on the larger scale. So the next thing will be about cost price and a bit about legislation. So how realistic is it to get it at a larger scale into place within the next 5 years, which is one of the targets of the project. Well, here are some of the assumptions, and I don't expect you to read them all, but you know it is a full cost price calculation. It's not the back of an envelope. And for instance, we've done everything on the 50 megawatt thermal input. So not a bigger one, even not if we would be at an industrial site. We consider 20% of the biochar as the yield, which represents 35% of the thermal input. And we use some of the finest wood chips you could get as the high end of the fuel price, the 100 euros per ton, with some 17 megajoule per kilogram lower calorific value. And we use some residual wood from composting, washed and chipped at the gate for 30 euros per ton. And that would only have not as much as 8 megajoules per kilogram. Then there is an option to use residual heat for drying in this case, where the residual wood from composting is quite wet.
So we have an investment of approximately 10 million euros for this 50 megawatt joule thermal input. And we make extra investments for the biochar case and also for the residual wood. It goes up in investment costs. Depreciation in 12 years, an interest of 5%, annuity of 11.3%. The OPEX we put on 6% of the investment, but with extra costs of 50 kilo euros per year for the residual wood, people sorting out the last bits of plastics, for instance. And we've put two different cases for the revenues of the heat. So this is the 8,000 hours in case of an industry or say city warming project, and then it's a industry. You could use the high temperature heat, which is worth more. It's 25 euros, whereas at the greenhouse, we only use 4,000 or 4,500 hours per year, and it's low temperature heat, probably something worth like 50 euros per gigajoule. So we assumed, and this is because then it's easier to make it visual for you, the biochar at a value of 350 euros per ton, and we see how this fits into the general economic schemes. So I will show you some of the cases that we do the calculations on, and because we have to do some of the subsidy schemes, we took the Dutch system subsidy scheme on heat, estimated for 2022 to be 8.5 euro per gigajoule. And we also tried to extend into the future, where we see what the effects could be of CO2 credits for the carbon storage in soil, and maybe for not using some European rights on the emissions. So if you would avoid the natural gas and you had emission rights, you could sell them also at this moment in time already at 50 euros per ton CO2 equivalents. So this is a lot of numbers. Just let's see how it works out. So this is the cost price. At a normal boiler, every time you get two columns, one is the cost and the next is the benefit. You see that if you have a normal boiler without any subsidy, even if it's 8,000 hours of heat delivery, then without subsidy, this fails to be an economically sound case. So this is common practice today. And you see that the green bar on the cost, which is the biomass, is huge. This is the finest biochar, finest biomass of 100 euros per ton. And even though the benefits in the second case for biochar from chips, the benefits are higher than just the heat, it cannot cover the costs. What you also can see, which is important for the next comparisons, is that in the first case, where you just have a normal boiler, which is combustion and heat delivery, the heat bar is larger because the biochar also presents a certain amount of energy value. So there is an energy content in the biochar, of course. Then if you would go to the compost residue, or even the compost residue dried with waste heat, there you can see that you have something that is very close or even on being economically viable. And that is mainly due to the fact that the biomass price is so much lower. So this is the range we're actually looking at, the lowest and the highest cost biomass. The capital cost is good to say is the lowest in the combustion case, the normal boiler combustion, that's the most left. And then it's maybe difficult to see, but this blue bar of the capital cost will increase towards the right. But you can see it doesn't have a big effect. The same for the variable cost, the orange part. It's the lowest on the left side. It will grow towards the right, but overall you can see the impact of the biomass cost is highest of all. So this is the case with the subsidy. It's the Dutch system of SDE++. And what you see in the left case is that the subsidy, which is now the green bar on top of the yellow, it fits the gap. And this is actually how the subsidy in the Netherlands is also organized, in that it takes off, it fits the gap, so it becomes an economically viable situation. If you would go to the next step, the biochar production in combination with energy, then you see again that you have a smaller yellow bar, which is the heat, but you have the revenues of the biochar, the blue, and then you have the subsidy, and maybe even you can, if you can make it happen, the CO2 credits for storing biochar into the soil. If the carbon storage credits these days go for 50 euro per ton, I don't see a reason why you would not get it for storing biochar in the soil after using it in the greenhouse. So this is sort of the current situation today, but the subsidy for bioenergy is you know, a bit under the magnifying glass, so to say. And what about this future possible scenario? It's just one of the things I came up with together with the people making the calculations for me. So what if we wouldn't have any subsidy on the heat, which might be the case for the future, but we would get carbon credits? What would it look like? And there you see the normal boiler, so combustion and just making heat. And say that if you would replace natural gas and you would have some ETS rights, which you could sell, then you would have the CO2 trading part on it. The question is if you would have it, if you would have the rights, the CO2 credit rights, and if there's anything to sell. If you would go then to the biochar case, you see that this is again for the 100 euros per ton biomass, the very, very most expensive ones. Your benefit column is a lot larger and is composed of more fragments, so to say, parts. As the less heat, then there is the biochar, then there is a possible CO2 credits from not using natural gas, and the carbon credits from storing biochar in the field. And you see it's getting there, but not quite. And so the 100 euros per ton might be still a bit too high for the biomass, or you could say the carbon credits are still slightly too low. However, if you go to the compost residue, there you see that both the drying with normal heat or with the waste heat, they are both very profitable. So it shows a much better business case, and it doesn't need even any subsidy. So anywhere between the price of 100 and 30 euros per ton for the biomass, I think for the NHR concept, we have viable business cases. The 100 not quite, but if you come a little bit lower, or if the CO2 trading prices would go a bit up, then I think without subsidy, you could run an NHR concept. Now, the downside is that we thought it would be so nice to put it at a greenhouse location, but there maybe you don't have enough hours of demand for heat during the year. Maybe you could take it to cooling, but for now we've taken 4,500 hours plus subsidy, and only so this 15 euros, so the low temperature heat price. And there you see that if you have combustion, it would, no, you wouldn't cover the costs. If you have the NHR concept with a high price biochar, you would also not cover the cost, but you would for the lower prices. So you see more easily, you will meet the requirements of having enough benefits to cover your costs. But the location at the greenhouse, if you can only sell your heat for 4,500 hours a year, that is not quite enough, unless you have very cheap biomass. And this is the same thing, but then, so the 4,500 hours without any subsidy, and this cannot be economically viable, not even for the compost residue. So just one slide on the legislation, because I think there we're moving quite nicely towards application. This is just a copied screen from the EU site, and as an annex to the new fertilization law, there will be biochar allowed as a product of pyrolysis and gasification to be amended to soil as either a fertilizing product or as a soil improver. It will come with quality criteria, but I'm sure that they will not be more strict than the European Biochar certificate, which we've shown you that we already meet. So there shouldn't be any problem, and the foreseen date of application would be July next year. So thereby, I want to come to some conclusions and recommendations. So produce biochar in co-production with bioenergy would be my main statement. In many aspects, economy and environmental benefits then also go hand in hand with the NHR concept. Environmentally and economically, it makes sense to go for large scale. And subsidy on heat, in my opinion, personally, is very likely to be replaced in the future by CO2 credit schemes. And then the co-production of biochar gives you a better business case. Only subsidy is needed. Now subsidy is needed all but in one case. There was the very cheap biomass and the 8,000 hours and high price for the heat. And another thing is that I think it's very beneficial and maybe even necessary economically to have this cascading approach, both for the economy and for the environment, where you first use the greenhouse substrate, the biochar there, and then use it after using the greenhouse as carbon storage in the field. I think in general, it is important to make a strong case then for carbon credits for biostorage in soil after use, because I don't see any reason why they shouldn't get it. And when choosing a location, choose a location with tradable CO2 credits that could help. Likely this is also larger than 50 megawatt thermal. So we didn't even model the larger scale, the 25 megawatt. It will be a lot better economically, as you have the economy of scale. A location which requires high temperature heat the year around is also highly favorable, because we've seen that 4,500 hours of heat delivery is not getting you there, except for the very cheapest biomass case. And constructing an installation for co-production now, I think, has less risk than 100% bioenergy installation for heat, in that you have more products, which means spreading the risk. You can have the idea of carbon credits for seeing more future-proof. And the nicest thing of the grade that we've chosen for scaling up is you have a fallback option to still produce 100% bioenergy by a minimum extra investment cost, because in the same concept that we've given you now, you can still use it as a fully combustion installation. And with that, I would like to thank you, and also the EU for funding it, as well as the Provincie Noord-Holland. And I want to thank also my whole team at TNO for doing an excellent job. Okay, that was it from me. Thank you.
Thanks, Rianne. I'm sure there'll be some questions in a few minutes. But But first of all, Laura's going to tell us about some of the tools that have been developed as part of the project.
Hello, let me show you the Horti-BlueC website. On the Horti-BlueC website, we are establishing an online collaborative platform. One of the features of that online platform is the decision tool. To get to the decision tool, go to the Horti-BlueC website and click Online Platform, and then Decision Tool. When you get to the Decision Tool page, click the image of the decision tool and it will open in a new tab. The decision tool shows you how a couple of residual materials can be processed or treated into new building blocks for sustainable growing media, energy, and CO2 fertilizer. The advantage of the tool is that you can access the information from different starting points. You can start, for example, from one of the residual biomasses and find out how it can be processed. But you can also start by clicking one of the processing methods or treatments. But you can also start on the right from one of the outputs that you want to obtain. To get more detailed information about the processing methods and the characteristics of the feedstocks, scroll down. If you have more questions or if you want to give feedback on the tool, click the contact button, write your email and your question or feedback and submit it. So I hope you will find the tool helpful and that you will enjoy trying it out. Another feature of the Horti-BlueC online collaborative platform is the mapping tool. The idea of the mapping tool is to map all stakeholders that are potentially involved in a valorization chain. So it can help to identify new connections within circular economy and to establish contacts between stakeholders to build a viable valorization chain. Currently, we have one map developed for shellfish contacts in the UK. This map can also be found on the Horti-BlueC website. Go to Online Platform and click Mapping Tool. Click on the image to open the mapping tool in a new tab. The map shows shellfish contacts in the UK. By clicking the symbols, you can get more information about the companies and organizations, such as contact details. For each of the valorization chains, Horti-BlueC has made a SWOT analysis. This SWOT analysis is actually the first step in illustrating the feasibility of the different valorization chains. A fact sheet with those SWOT analysis can be found on the Horti-BlueC website. Go to Project Outputs and then go to the valorization chain page. If you scroll down on that page, you can find PDFs with the SWOT analysis which you can download. This is what the fact sheet for valorization chain 1 looks like. For each of the valorization chains, the fact sheets report the strengths, weaknesses, opportunities, and threats of one or more new solutions proposed by Horti-BlueC versus a current baseline scenario. So please go visit and discover our website and find out more about the valorization chains and the project in general.
I know Bart has a few closing slides.
Okay, thank you, Krista. So we are almost at the end of the webinar and we have some final announcements for you. So as we speak, you will receive a mail from us with a link to a questionnaire with some questions related to the webinar of today. So if you can give your opinion on the webinar, you can check all the data that we have processed, because you will find links to the video or to a fact sheet or to the decision tool. And if you have any remaining questions, you can also put them in the questionnaire, and we can use this to further contact you and to give you the answers that you would like to have. So please fill the questionnaire. It takes only a few minutes, so maybe do it directly after the webinar. So then that would be nice for us as well. So if you like this kind of webinar, we have 2 others in the coming week. So we have one on chitin production from shellfish waste. It's on May 20th. You can still register for that until Friday this week. And then in June, we also have one on reusing spent growing media by direct reuse or as feedstock for biochar or compost. So you still can also register for this webinar. And if you still want to know more about the project, we have 2 open events which are planned in the coming months. We have an open event in Ghent in August, and we have an open event in Portsmouth in October. And here we will more focus on the results of the greenhouse trials. So that's important to know. And if you still want to know more about growing media, there is even a whole symposium planned for this summer in Ghent, where you can learn a lot about the ongoing evolutions and trends in growing media research and the sector. So, and if you want more information about the different building blocks that we have developed in the project, like the chitin, the biochar, spent growing media, green compost, plant fibers, we have several videos and papers, and also, of course, the decision tool. So please use these links to access this information and provide us with your feedback. So that's all for this information. So thank you for being in this webinar. So we have different ways that you can further check our results or get in contact with us. And I would like to give the word back to Cressida.
Thanks, Bart. And just a final thank you to all our attendees for coming along and for participating in the polls and in the discussion. And we hope to see some of you at our next webinar. So yes, thanks very much. Goodbye.